Have you ever used an AI and just, marveled at what it can pull off? Generating really complex text or drafting code, even writing stories that feel, well, intelligent. It really seems like these large language models, LLMs, are solving problems almost effortlessly. But here's a question that got us thinking. How well do they really understand what they're doing, especially with something as rigorous, as logical as high-level math? So today, we're doing a deep dive into this fascinating area, LLMs trying to tackle Olympiad-level inequality proofs. Seriously challenging stuff. And we've got some pretty cutting-edge research here that highlights a critical and honestly quite surprising gap in what AI can currently do.
Exactly. And our mission for this deep dive is pretty clear. First, we'll unpack why these specific math challenges are so uniquely tough for AI. Then we're going to introduce you to a really groundbreaking new benchmark. It's designed to genuinely test LLM reasoning in a way that hasn't really been done before. And finally, we'll reveal the surprising, sometimes almost comical ways these advanced AIs can stumble, even when they somehow manage to get the right final answer. So by the end, you'll have a kind of shortcut to understanding the real nuances of AI reasoning and what it means for, well, the future of reliable AI.
Okay, so let's get into it. We see these LLMs doing incredible things with language, right? But then comes high-level math. Why is that such a different beast for them? What is it about mathematical inequalities they seem like just logical puzzles? Why are they such a hurdle?
Yeah, that's a great question, and it really gets to the heart of it. While LLMs are trained on, well, just unimaginable amounts of text, natural language, mathematical reasoning requires something different. It demands sound deductive steps, rigorous step-by-step logical progression. It's not just about finding patterns in the data or generating text that sounds plausible. Language often works on association, probability. But math, especially proof, is about certainty, logical necessity.
Okay, so it's a fundamentally different kind of thinking.
Precisely. And a major bottleneck for developing LLMs in this area has been, frankly, the lack of good training data. Suitable datasets. Existing ones often fall short. Some general AI theorem-proving collections might have very few inequalities. Others might be synthetic. But they lack the kind of structural diversity you see in real math problems, and curated ones, often just too small.
Right, so the training material itself has been a problem. And I think you mentioned something about the format of the data, too, this fully formal versus informal distinction.
Ah, yes, excellent point. Many existing datasets use these fully formal representations. Think languages like Lean or Isabelle. They are incredibly precise, like writing perfect legal code. Every single step has to be justified according to strict logical rules.
Super rigorous.
Exactly. But LLMs, because they're trained on natural language, are generally much better at what we call informal reasoning. That's closer to how humans often start thinking about a problem using natural language, maybe some intuition, before formalizing it.
So trying to force them into that super strict formal system is like...
It often trips them up. It's like asking someone who's brilliant at conversational English
Yeah.
to suddenly write flawless legal code from scratch.
Ugh.
The rigid syntax, the absolute precision required,
Yeah,
it's just not their native environment.
got it. Okay.
So to bridge this gap and to really test LLMs in a mode that might suit them better, this new benchmark was developed. It's called InequMath, and it's specifically designed to explore and test these informal mathematical abilities, much closer to how a human mathematician might initially approach things.
And this is where it gets really interesting, right? The way these problems were created, not just standard textbook stuff.
Not at all. The InequMath problems were actually crafted and then reviewed by IMO-level medalist experts.
International Mathematical Olympiad medalists. Wow.
Yes. So these aren't problems the LLMs would have likely seen before in their training data. They're novel. They're designed to be genuinely challenging. The benchmark includes 12,252 training problems and 200 really tough Olympiad-level test problems.
Okay, and they're presented differently, too. More like how humans write math.
Exactly. They're presented in informal language, mimicking how math is often written and discussed, and they come in two main formats, multiple choice, MC, and open-ended, open, where the LLM has to generate the full solution. Plus, each training problem is annotated. It shows relevant theorems from a list of 83 named theorems across 29 categories and gives step-by-step solutions.
Can you give us a flavor, like an example?
Sure, so imagine a relation problem you might be given. Let ABC be positive real numbers such that ABC1, standard setup. Then it asks, determine the correct inequality relation, like greater than, less than, or equal to fill in the blank between this expression B plus CH4T plus C plus A plus B out TC, and this other one, scored A plus scored TB plus scored TC plus 3.
Okay, definitely not simple arithmetic. You'd need some deeper insight there.
Right. The answer involves recognizing you need to apply something like the AMGM inequality. It requires insight, not just calculation.
Where you mentioned bound problems.
Yes, where you have to find the largest or smallest constant, let's call it C, that makes an inequality hold true. For example, let ABC be non-negative real numbers. Find the largest constant C such that A2 plus 1, B2 plus 1, C2 plus 1 equals A plus BC plus K, ABC2 plus K but C.
Whoa. Okay, that looks seriously tough. These are clearly designed to push the boundaries.
Absolutely. They demand deep understanding and often quite complex multi-step deduction. Now, evaluating the LLM's attempts at these problems, that's where the research introduces a really key innovation, the LLM-as-judge evaluation framework. Because they recognize something crucial. Just getting the correct final number or relation isn't enough. The process, the reasoning has to be sound.
Right, because you could just guess the right answer or get there through faulty logic. So an LLM judging another LLM, how reliable is that? Does it work?
That's a fair question, and one the researchers were very focused on. They found it surprisingly robust. It achieved a high F1 score that's a measure of accuracy of 0.93 alignment with human expert annotations.
0.93, that's pretty high alignment.
It is, and crucially, it's scalable. Imagine trying to get human IMO medalists to manually grade thousands of AI solutions step by step. It's just not feasible. This framework makes rigorous evaluation possible at scale.
Okay, so how does this LLM-as-judge thing work? Is it just one judge?
No, and that's key. A solution is only marked overall correct if it passes all 5 judges. There's a high-precision final answer judge checking if the final result is right, but then there are 4 specialized, stepwise judges. These were specifically designed, based on pilot studies, to catch common types of reasoning flaws that LLMs tend to make in these kinds of proofs.
Okay. So it's not just right answer, but right answer and valid steps.
Exactly. And here's the kicker, the really critical insight from the study. While the top LLMs, models like Grok 3 Mini and O1, achieve much higher final answer accuracy, like Grok 3 Mini got 71.5% right answers compared to maybe 37.5% for a general model like GPT-4o.
Which sounds impressive on its own. 71.5% is pretty good.
It does sound good, but their overall accuracy, which measures both the correct answer and the soundness of every single step, that was substantially lower.
Substantially lower. How much lower?
Significantly. It means they were often stumbling through the steps, making logical errors, invalid assumptions, calculation mistakes, even when they lucked into the right final answer.
Wow. So it's like watching someone walk a tightrope, right? They might wobble and almost fall off multiple times, but somehow they make it to the other side. You wouldn't say they walked it perfectly.
That's a perfect analogy. You wouldn't trust their method, even if the outcome was okay that one time.
Okay, this is fascinating. So what are these flaws? What kind of reasoning errors are these stepwise judges catching?
Right, that's the next important piece. The researchers identified several common pitfalls.
Let's break some down. You mentioned inappropriate reliance on toy case examples. What's that about?
Yeah, this is a big one. The LLM might test the inequality for a really simple specific case. Like if you have variables ABC, it might just check what happens if ABC1 or ABCT. It finds the inequality holds for that one simple case, and then it sort of jumps to the conclusion that it must hold universally for all possible ABC.
Ah, I see. So it assumes a specific example proves the general rule.
Exactly. For instance, in one problem, to find a constant C, an LLM correctly minimized a function only for the symmetric case ABC and concluded C4. But that only proves the inequality works for that very specific narrow slice of the problem's domain. It doesn't prove it for all ABC. It's a logical fallacy in a proof context.
Right. Okay. So for you listening, if an AI gives you a solution based on one simple example, be skeptical. It might not hold true more generally. What else?
Another one is unaddressed logical gaps. This is really interesting. It's where the logic itself has a hole. An LLM might say something like, without loss of generality, or WLOG, let's assume YZ line. When dealing with variables XYZ, that could be anything in a range.
Okay. Mathematicians use WLOG sometimes, right?
They do, but only when they can justify that simplifying assumption doesn't actually lose generality. You have to argue why solving the simpler case covers all cases. The LLMs often just make the assumption, like setting YZ1 without any justification. They just narrow the problem domain arbitrarily.
So they haven't shown that solving it for YZ1 tells you anything about the case where Y2 and Z3, for example.
Precisely. It makes the argument unsound right from the get-go. The judge might sometimes miss this, accepting the restriction as valid, which highlights the subtlety here.
Okay, what's another common flaw?
Unjustified numeric approximations. This one seems subtle, but it's really important for mathematical rigor. The LLM might calculate some exact symbolic value, maybe involving roots or exponents like 3779-16. Then, instead of using that exact value, it calculates a decimal approximation, say 1.0845, and then it uses that approximation as if it were the exact bound needed for the proof or the final answer.
Okay. So even if the approximation is really close, like 1.0845 versus the true value,
Right.
using the approximation as an exact boundary in a proof just isn't valid. Proofs demand precision. You can't round halfway through and claim rigor.
Exactly. It undermines the logical certainty. The judge evaluating this might struggle sometimes to tell if an approximation is just for illustration or if it's improperly used as part of the core argument.
Tricky. And the last one you mentioned was almost basic.
Yeah, it's almost jarring. Just
Yeah.
plain numeric calculation errors, simple arithmetic mistakes. In one example, an LLM correctly set up the whole inequality, did the hard conceptual work, but then calculated 12/3 is 16.
Instead of 18. Ouch.
Right. Now, in that specific instance, calculating it as 16 versus 18 didn't actually change the direction of the final inequality. So the final answer looked okay.
But the step was just wrong.
Fundamentally wrong. It highlights a flaw in the execution and the reasoning process, even if the final output seemed right by chance.
It's like, yeah, getting the right address on your GPS, but the directions involved driving through a lake. The process was flawed.
Exactly. So, okay, given all these potential pitfalls, these sort of surprising ways LLMs can fail even while seeming to succeed, how do we help them get better? What strategies can improve this rigorous reasoning?
Yeah, what did the research find there?
Well, one strategy they explored was providing relevant theorems as hints. The thinking was maybe if the model knows which mathematical tools are likely useful, it can apply them more effectively.
Makes sense. Like giving a student a clue. Did it work?
The results were actually quite mixed and really fascinating. For weaker models, giving them one or two relevant theorems sometimes decreased their overall accuracy.
Decreased. Why would that happen?
The hypothesis is they might get confused, misapply the theorem, or get distracted by a hint they don't fully understand how to integrate into a proof. Information overload, maybe?
Okay. But what about the stronger models?
For the stronger models like Gemini 2.5 Pro in their tests, these hints did help. They benefited from knowing the relevant theorems.
Interesting. So the ability to effectively use a hint depends on having a certain level of underlying reasoning capability already.
It seems so. It really underscores that just throwing information at the problem isn't enough. You need more sophisticated ways for the AI to retrieve and properly apply relevant knowledge.
It's like that analogy you used giving a complex recipe to a novice chef versus a master chef. The master uses it for inspiration. The novice just gets lost.
That's a great way to put it.
So let's zoom out a bit, connect this to the bigger picture. Why does this specific research, LLMs, trying to solve niche math inequalities, why does it matter beyond just, academic curiosity?
That's the crucial question. I think the most significant risk here stems from potential over-reliance on AI-generated proofs or analyses that look correct on the surface. But as we've seen, might contain these hidden critical logical flaws.
Right. Imagine someone using an LLM for, I don't know, designing a bridge or complex scientific modeling or financial analysis, fields that demand real mathematical rigor.
Exactly. If a flawed proof generated by an LLM is used uncritically, it could lead to seriously incorrect conclusions, faulty engineering designs, flawed scientific theories, maybe even significant economic miscalculations. The consequences could be severe.
So the fact that they can get the right answer sometimes, but through shaky reasoning, that's the real danger zone. Precisely. And that's why developing rigorous, stepwise evaluation methods, like the LLM-as-judge framework, is so important. It's a contribution towards mitigating that risk. By promoting transparency about the reasoning process, by enabling us to identify these fragile chains of logic, it encourages more cautious deployment. It really emphasizes the need for human oversight and verification, especially when the stakes are high. And releasing the IneqMath benchmark publicly helps the whole research community work on improving the reliability of AI reasoning.
Okay, So, wrapping up today's deep dive, we've journeyed into this surprisingly complex world of LLMs tackling high-level math proofs. And we saw that while they can often get the right final answer, the path they take to get there, it's frequently filled with these subtle logical pitfalls, calculation errors, and surprising reasoning flaws that you might not spot at first glance. Yeah, understanding these flaws, things like overgeneralizing from simple toy cases or leaving unaddressed gaps in logic or making calculation errors, it's really vital for anyone who's starting to rely on AI for critical thinking tasks. It's just such a powerful reminder that, especially in AI right now, a correct answer doesn't automatically mean sound reasoning. The process matters immensely.
So maybe the final thought for you, our listener, is this. As you encounter more and more AI-generated content, whether it's solving a problem for you or explaining a concept or writing a report, ask yourself, how much do I trust the process that generated this answer, not just the answer itself? And maybe what steps could I take to actually verify the reasoning behind it? That's all the time we have for this deep dive. Until next time, keep questioning, keep learning, and keep diving deep.